So,
Hello, guys.
hello, Moon, Igor. Uh,
Hello.
could you please introduce yourself? Let's start with you, Moon.
First, thank you for having me here. And my name is Moon, and I've been working on open source project for a while called Apache Zeppelin, and I have a lot of passion on the open source software and the community. And recently, I studied a service called Staroid, and today like to share on our experience, how we built some service, serverless experience for Apache Spark on top of a Kubernetes cluster.
So, and you, Igor?
Yeah, I'm working at a company called Klarna. We do financial services, and I work in the data domain and in a team that is responsible for data responsibility. So I'm very interested in this sort of things that Munsali is going to talk about. And I have some experience with Spark and Kubernetes, but never with Spark and serverless approach and running it on Kubernetes. So I'm looking forward to this talk.
So, Moon, who will find your talk the most useful? Who is the audience of your talk?
I think that's a good question. I think, of course, someone who likes to use Spark, or someone who in the company as a DevOps, for example, a lot of company trying to have an internal Spark service for. So that might be a good audience to get some information, useful informations. Or if you are a data scientist or a machine learning engineer who likes to use Spark, and you can also get some useful information from this talk, I think.
So, what will the talk will be about? Could you please explain very briefly, not to spoil everything? That would be good.
Yeah. First, I think Spark serverless is actually an experience. I think it's not really a particular technologies or code, but it's more like an experience. And we will talk about how Spark serverless experience is different from just a traditional way of using Spark, and why it benefit. And of course, we will talk about how we how we built this experience on top of Kubernetes.
So, okay, we have just 30 seconds before start of our time slot. So let's switch to the talk. Dear operators, please switch the layout to the new one. Yeah, nice. So now you can talk, Moon.
Okay. Let me start talk. Today I'm going to talk about how we built Spark Serverless on top of Kubernetes, and we already did an introduction, so I will skip this part. But later of this talk, I think if we have a little bit of time, I'd like to also discuss about my motivation on starting this project, and why I think it helped on open source community in general. Let me first explain what traditional Spark experience look like compared to Spark serverless experience that we like to build. So traditional Spark experience is first. I assume audience here is a little bit familiar with the Spark cluster, but if you are not, I think it's not a big problem. You can just understand briefly how Spark works today. So first, I think when user want to run any task in the Spark cluster, of course you have to have a connectivity to your cluster to submit a job or to access the Spark UI, or so basically you need a network connectivity. And of course, that depends on your infrastructure, where your Spark cluster is running or is going to run. So if it is a cloud environment, you probably want to prepare VPN connection or configure your subnet and security group or firewall. So you spend time on network configuration, and sometimes you need to get help from DevOps or infrastructure management people. So that's one thing. And another one is then you like to connect to your Spark cluster. To do that, you either need to spin up your Spark cluster, or you need to find a Spark cluster that is already running and allowed to use that. And then, of course, you need to submit a job, your job to the Spark cluster, and that, of course, requires network connection. And to submit a job, you need to package your applications, and then you can finally submit on your Spark application, and Spark cluster runs your job, and then you will able to see the result once job finishes. That's, I think, it common experiences on Spark cluster nowadays. But what we wanted to have was actually we wanted to make user doesn't have to know about anything about network, anything about the cluster, don't have to have a help from DevOps, or don't need to aware of how Spark cluster is configured on the server side. So what we wanted to have is a user just need import a library or a Spark library and write a Spark API, Spark code, and run, and that automatically runs on the cloud side. So that is the experiences that we wanted to build. So that's what we call Spark serverless experience, because the user doesn't have to worry about server side of environment from the network to actual Spark cluster. Doesn't mean there is no server side of instances, but it means that users don't have to aware of that. So first, I'd like to actually show how it works, and so you will have a better idea on it, and then we will go through how we implemented and what are the problem we met and how we solved the problem. So let me first go through the demo, how it actually works. So in the demo, I will show I will use two different environments. One is a shell, Python shell, and another one I'm going to use is a notebook. So they are basically the same, but have a slight little bit of difference on accessing Spark UI that I'm going to explain. So just I wanted to demonstrate both environments. So you have a better idea on how you can actually work, how it might work on your actual daily work. So first thing is we will going to explain detail architecture and how we build. But first, let me just create a Kubernetes cluster, because we are going to build this environment or serverless experience on the Kubernetes. So first, let me create a new environment, a Kubernetes cluster called Smart Data. And also, I need an access token to this environment. And let me use this one. So this one is this access token, and creating Kubernetes cluster is specific to this service called Steroid, but you can, we will explain later. So first thing I need to do is I need to export this access token. And then I need to install a library. So this library is called ODS, and it stands for Open Data Studio. This is an open source project, and we actually implemented this Spark serverless experience and service code. We released this service code as an open source. So this is a client package for that. So actually, everything is now ready. So I just install the client library, and I exported my access token, and that's all I need to use this to begin this Spark serverless experience. So let me actually try use it. So I just run Python repo, Python shell, and I can import this library, and I can initialize this library with smart data. That smart data is the name of a Kubernetes cluster that we created, and then I can get a Spark session. So let me name my Spark session to demo 1, and I like to have a 2 initial Spark workers. I can actually omit this parameter, then Spark will automatically scale, but I like to start with the two executors, and I like to use Delta Lake configured, and I can get a Spark session, and I can assign Spark session to Spark variable. I think I missed to install one library, and let me try it again. Okay, because in case of every time demo have a demo slot, so I fortunately I have a backup environment. So let's first try notebook from the notebook actually. So it's basically same from the terminal. Only thing I need to do is I need to set up my environment variables here with my access token, and then let me try run this one. And rest of the step is the same. Actually, I can set my Kubernetes cluster name either from the environment variable or the parameter of init function. And then I can name it to demo 1. And it will, behind of it, it will create namespace and instances of Spark executors on the cloud. So to check, to see what's going on, I can open a separate window on the side, and I can go to the management console and see my cluster instance. And we can see from smart data cluster, Spark Kubernetes cluster, now have a demo 1 serverless Spark instance. And for the user, we are not really aware of all of this. We are just using, we just got a Spark session. And let me run Spark API here. This is just create a data frame and generated 10 records and display the data. So it works like this, and we can actually do a little more complicated work here, such as loading data from cloud storage like S3 and run Spark SQL against the it. And of course, as expected, it can display a result in a second or in a minute. So what's happening behind of it is a Spark application is actually Spark driver is running Spark application consists of a Spark driver and executors, I think. And in this case, Spark driver is running on this Python environment. This example, Spark driver is running on Google Colab notebook, and Spark executors are running on the cluster remotely. And we can also access Spark UI and see how our job is executed here. So this is an experience we like to provide to the users. And I really wanted to show the terminal version of in terminal how it works, but somehow I think I just messed up my environment. But you can see from notebook, which is also a Python interactive environment, how Spark Serverless works and what the experience will look like. Users just need to set up a basic information such as an access token and import library, and that's it. Basically, all users need to do. Don't need to aware of anything, but just get a Spark session and use that session, and then everything will taken care automatically behind. So sure. Yeah. Yeah. Actually, there is a Spark conf argument in this function, so you can pass the dictionary to configure additional parameters. And this ODS library, Open Data Studio library, is actually an open source that we open sourced. So if there is some features that lacks, then of course you can contribute and add. Right. Right. That's I think also something that we need to work on actually. So one way is using Spark Conf, we can pass some parameters to load additional libraries. Well, but one thing that we think it's maybe better, but we are not quite sure yet, is for example, this is one example of loading Delta Lake library. Is of course I can manually add all the jars and configurations necessary to enable Delta. But another way is we can make it simple. So just adding a flag, Delta equals true or false, And when Delta flag is set to true, then internally we set all the jars and configuration that to enable Delta. The reason why we start in this way is because of Spark version might be different. As you can see, actually, we can user can select Spark version, and depending on Spark version, Delta the dependency version might be different, or configuration might be different. Also, Python version might be different, the local Python version. So some configuration depends on the Python version. So we don't know what's the best way to do, but I think one possible way is like we see here, Delta flag. So add a one flag that automatically configure all the necessary, automatically changes all the necessary Spark configuration underneath. That's one way. But of course, I think for there must be a use case that user want to fully customize their Spark or Spark configuration. So that's it. I think that's why we still kept the Spark conf parameter here. Okay, let me come back to the slide, and let's see how it actually works and how we built. So first, let's take a look at Spark on Kubernetes. Spark on Kubernetes is Spark on Kubernetes is included in Spark since I think 2.4, around 2.4 version. But and when we see a Spark on Kubernetes, we thought it's really good because it actually simplifies a lot of cluster maintenance job. As long as you have a Kubernetes cluster, using Spark on Kubernetes is really simple because of a cluster management operation or maintenance overhead is actually offloaded to the Kubernetes side, and Spark just spin up their executors or a driver inside of a Kubernetes cluster as a pod. So it really simplifies maintenance of a Spark cluster. So we thought maybe we can directly use Spark on Kubernetes to implement Spark serverless experience. And to use Spark on Kubernetes, we need your application or Spark application need a couple of informations to run on the Kubernetes. First one is, of course, Kubernetes API server or access to the Kubernetes API server. And the second one is you need a Spark container image. Of course, Kubernetes run everything on in the pod, and the pod runs containers. So you need a container image to run. And of course, your application itself, application artifact. And then one last thing is once you submit your application, then your Spark driver and executors are running on inside of Kubernetes cluster. So they need to communicate each other. So usually, if you just submit your application in the cluster mode, and you don't have to worry about this actually, network access between driver and executors, because they are anyway running in the same Kubernetes cluster. But our experience, the serverless experience we want to give is requires driver run on the client side on your laptop or some environments that you control, but executors running on the Kubernetes cluster that is running on the cloud remotely. So we need that's some differences that we need to solve. So once we use Spark on Kubernetes, we can submit a job. But if we can keep our client in user's environment and just letting executors running on the Kubernetes side, that's almost exactly the experiences that we expect from Spark serverless. So we decided to use Spark on Kubernetes directly, but just wanted to move Spark driver out of a Kubernetes cluster and letting driver run on users' environment. So user can have an interactive Spark experience, serverless experience, instead of user. The other side of experience is submit a job into the cluster and wait until that finishes and retrieve the results from your file system. Yep. Yep. Right. Right. So drivers collab, we have a Spark session variables in collab, right? In our Python environment in collab, and Spark session is basically attached to the we can see Spark session as a representation of the Spark driver underneath, and that means Spark driver is running inside of our collab Python environment, and executors are running remotely on the cluster.
So if I have a big data frame that I want to collect to a driver, I need to be sure that my research instance has enough memory and stuff like that, right?
Right, that's right. So if you collect all the data to your Python variable or to Python memory, of course, you need the memory size of the data you like to collect. But all the Spark API or Spark operation, Spark data frame operation or RDD operation, they will still run on the cluster side.
Yep, thanks.
Yeah, and this is actually kind of high-level architecture, some abstracted version of architecture we end up with today. We will deep into one by one this component, but first let me explain briefly. So we support multiple multi-cloud Kubernetes cluster, and users application, Python application, can connect to this Kubernetes cluster in a secure way. And we are using a tunneling mechanism here that I'm going to explain soon. And we also have a automation controller to help to have a secure environment or secure multi-tenant environment. And also we had to taking care of our Spark container image to support multiple versions of Python. So this is a kind of brief architecture that we have, and let me drill down one by one here. But first, I'd like to list out the problem that we met during while we are building this experience. So first problem we met is a problem around isolation or multi-tenancy. Because of we wanted to share Kubernetes cluster among multiple Spark application or multiple users, because each user having separate Kubernetes cluster for each application or each user is probably that's too much. So we like to letting our Kubernetes cluster run multiple users' tasks. And then, of course, we need an isolation or multi-tenancy between those users or applications. And here, the problem is the default configuration. Most of the default Kubernetes configuration, each pod can communicate each other. That means executors of Spark that is running capable of running arbitrary code from user. I can create a UDF, or I can create my custom mapper or reducer for my RDD, and I can run submit that task. And then my executors are running my custom code. That means executors can potentially access to other applications, driver or executors, which we don't want to do. And also, we also need to limit or apply a quota to a certain application or user. So a particular user, we wanted to prevent particular user consume all the resources in one cluster. And the second problem is, of course, we wanted to run Spark driver outside of a Kubernetes cluster. So when driver runs inside a cluster, like this diagram here, and that's not a problem because driver run in the same cluster as communicating with the executor is not a problem. It's not difficult. But if you want to move this driver out of the Kubernetes cluster and run remotely, we'll need to make some connection between driver and executors. But we wanted to make it really, really simple. So user doesn't have to aware of anything about the network configuration, doesn't have to have knowledge on network configuration, doesn't need to help from any person who manages the cluster. That's what we wanted to do. So we wanted to make a really easy easy network connection on user's perspective. And also, the requirement of this network connection is actually need a bidirectional communication, bidirectional connections, because of executors actually initiate connection to the driver, and driver also initiate connection to the executors. So this network connection should allow discovery of executors and driver each others. So if we take a look, the solution for these problems, Kubernetes, fortunately, Kubernetes provide a lot of features that can solve these problems. So on the multi-tenancies and isolation side, Kubernetes supports network policy. We enabled network policy, so we can apply network policy to our namespace. So you can actually apply your network policy to the namespace or any label that you want to have in the Kubernetes. But in our case, let me go back to the slide here, and you can notice that each Spark application have their own namespace, and we apply all the security or isolation on namespace scope. So that's why our design. You can try apply isolation on your pod level, or you can apply some label for global pod, and you can try apply those isolation on the scope of your global pod. But we decided to apply this isolation on the namespace scope. We thought it's easier and easy to manage. So we applied network policy to the namespace level. That allows, that blocks all the communication between different namespace of Kubernetes, Spark cluster running on the Kubernetes. So that guarantees no driver or executor access the other applications, drivers or executors. Another one is we also wanted to aware of container security. Actually, container is already an isolation of your workspace or your process space, but we thought it's not really perfect in terms of the security. There could be some exploit or some vulnerability of container technology itself. And if a user can escape from the container and access to the host machine, and that will open a lot of chances to access the other users' workload, other users' container. And we wanted to prevent that happening as much as possible because of our cluster is multi-tenant cluster and multiple users' workload is running in the same cluster. And we don't want to happen this container, container escape their boundaries and access the host machine. So first thing we did is, of course, apply the pod security policy on the Kubernetes and remove the root access. So all our Kubernetes cluster pod executors and executor pod is running without root permission. So that's it. I think the minimum thing that we wanted to do. But another additional protection we wanted to do is we actually wanted to have we wanted to allocate each executor VM. So one executor holds one VM, and VM here is equivalent to the Kubernetes node. So one executor runs on one Kubernetes node, and that particular Kubernetes node doesn't run any other executors. So one VM runs only one executor. So even if executors able to exploit the container and access to the host machine, that host machine doesn't run any other users' work. That's what we wanted to guarantee. So to do that, we took a look the way to make it happen in the Kubernetes. So you can think it as a each pod or executor pod have a dedicated node, dedicated VM allocated. So to make it happen, we first tried actually implement this one using pod affinity feature in the Kubernetes, but we realized that in a large scale cluster, Kubernetes scheduler is having a hard time dealing with the anti-affinity rule. So we tried to find the alternative, and we found very easy workaround, which is each pod, if we assign a host port, the same host port on each pod. The host port in Kubernetes means the port is connected to the host machine's port. And if we allocate host machine's port number in each pod of executors, and of course, a particular port number is only one particular port is available on each host machine, and pods that have a same host port assigned cannot be allocated in the same VM or same host machine by Kubernetes scheduler. So in this way, without having very complex rule or expensive rule, we can just set all the same host port in all the same executors, and then Kubernetes scheduler will automatically allocate each pod in a dedicated VM or dedicated Kubernetes node. So to do that, we wrote automation webhook or mutating webhook that you can see. This is also part of a Kubernetes API or a way you can extend Kubernetes feature. That is once Spark want to create a new executors, and then automation webhook actually mutate your Kubernetes executor definition and automatically add this host port. So in this way, actually Spark application doesn't have to handle this one. Kubernetes cluster will aware of these executors, and Kubernetes will automatically add this definition to your executor request. So in this way, we could able to guarantee that its pod is running in a separate machines or VMs. And another one is we like to apply resource quota. So prevent kind of, DDoS, or we don't want to one application consume all the resources. And this is, I think, one of the benefit of allocating one namespace for each Spark application is, I think it's easier to apply resource quota in Kubernetes, because it's much easier to apply resource quota in a namespace level than the others. And in terms of network connections between driver and executors, we wanted to make it as invisible as possible for the users. So everything, we wanted to make it happen automatically in the most cases. So we like to, the way we did is using the tunneling mechanisms or tunnels over HTTPS. So we run tunneling server on the Kubernetes side, and that tunneling server and also tunneling client is automatically initiated when you import the client library and initialize that library. And tunneling client will initiate connection to the tunneling server. It's only HTTP connection. So even if a user have a firewall, a user is behind the firewall or behind the NAT or inside a corporate network, as long as the network allows to browse, web, just a standard HTTPS port, user's client will able to create these tunneling network tunnels. And once network tunnel is created, and then inside through that tunnel, bidirectional connection is possible through this tunnel. So actual tunnel connection is, in user's perspective, it's only egress connection. But once tunnel is established, then inside the tunnel, bidirectional connection is possible. So in this way, Spark driver running on user side able to reach to the Kubernetes API server, as well as executors running inside of Kubernetes. Also, Kubernetes executors running inside of a Kubernetes cluster can reach out to the Kubernetes driver running on user's machine. So that's it, how we set up this tunnel. And to enable this, we also have a Spark configuration a little bit optimized for Spark on Kubernetes. I think nowadays there are a lot of slide or tips for Kubernetes, Spark on Kubernetes. So we follow the best practice. For example, enabling shuffle tracking and such a couple of different parameters that helps running Spark executors on the Kubernetes. And I will not go into the detail here, but setting up right parameters make a big performance difference, especially when executors is when scaling down the executors. So scaling down executors means some executors will lose their shuffle data or local data, and that can be expensive. So adjusting a couple of parameters here really helps that. And another side of this experience is, I think, a client library. And client library is very important because of we like to give a good experience, very smooth, simple, and easy experience. And client library should handle all the network connection and Spark initialization and so on. So user doesn't have to care about all the complex things. And how client library works is in this way. So first, when user import and initialize client library and try to get a Spark session, then the client library downloads Spark binary locally. So because of we don't want it to have some complex Spark configuration in the client side as well. So we don't want to require user to download Spark separately and configure Spark home variable and copy the Spark configuration. We don't want user to do anything of that. So client library automatically downloads Spark binaries. Of course, it also configure tunnel that we explained just before, automatically configure the tunnel and detects the local Python versions and configure to use the right version of Python in the container remotely. We will explain this later a little bit more. And then, of course, initialize the tunnels and the Spark drive, and that will communicate with the Spark Kubernetes API and will initialize the necessary executors on the cluster side. So client library is, I think, playing very important role to provide a seamless experience. And another one that we realized is actually PySpark is especially depends on Python versions. So once, for example, if driver runs on Python 3.6 and executor runs on Python 3.7, it doesn't work well. So at least the driver version and executor's Python version should be matched. But again, we don't want to user to choose particular parameters or configure on server side or Kubernetes side to use Python 3.6 and switch to Python version. And we don't want to user to do anything. We want it to do everything happen automatically. So what we did is in the container image, we built our custom Spark container image, mainly because of we wanted to ship multiple Python environment by default. So our container image build script includes creating multiple Python environment inside of image. So later in the client can just configure target Python environment path after detect the local Python version. So in this way, we currently support Python 3.6, 7, and 3.8. But in this way, we can add more Python version support, and it's handled automatically on the client side as well as the server side. So user doesn't have to aware of that, aware of matching Python version. So this is how we built Spark serverless experience on top of Kubernetes, and you can hopefully you can see some benefit of it. And if I summarize the benefit that that we wanted to provide, and we actually got from this implementation, is actually for user side, user's perspective, especially for data scientists or machine learning engineers, they can spin up Spark cluster or Spark executors really easily. They don't have to, they don't need help from any other person or any other people. They can just import library with their access token, and they can run their Spark job interactively. And when they finish their job, everything, executors and everything is automatically terminated. So it's not only easy, but also it also helps resource utilizations because of some use case. I think some company have a Spark cluster, large cluster, and that's a shared cluster, and all the users submit us up to the cluster. And yeah, that's not too bad because the Spark cluster can also scale out and scale down, but it's not. Sometimes it's not really easy to share one cluster because sometimes you load particular libraries, additional library, or want to use different clusters. So I think it gives much better resource utilization overall when each application have their own set of executors, or each application can have their own clusters. So in this way, we could enable that. So we have a better security or isolation because of each application have their own Spark cluster. So you don't have to worry about other user screw up the shared cluster, or other users, break something. And another one is actually we are still working on this to make it faster. So spinning up Spark cluster is actually really fast. So all you need to do is, or all this Kubernetes cluster need to do is just creating more executor path. So as long as your Kubernetes cluster have a room to create more executors, and your executor container image is loaded, it's just a matter of seconds to add more executors. In case of your container image is not yet downloaded to your Kubernetes cluster, or your Kubernetes cluster need to scale out, yeah, it depends on your cluster, but it usually takes 1 or 2 minutes to that happen, provisioning a new node and download the image. But I think it's okay in most cases. But we are actually working on predictively warming up additional Kubernetes node and pre-warm the container image. So in the 90% of case, or the most of the case, user doesn't have to even wait those 1 or 2 minutes. Just a few seconds, always user able to have their Kubernetes executors or clusters that they want. So this is it about how we built a Kubernetes cluster, Spark serverless experience on Kubernetes cluster. But I want to mention a little bit about why we did on service called Steroid, and whole initiative behind of it. So the Steroid is what I'm working on at the moment. And this is a cloud platform for developers and enterprise users, especially open source developers. The reason we start to build this platform is because we thought there is a gap between open source project and users, especially enterprise users. Because of open source is really great. I really love open source and how open source community works. But what it lacks is open source community cannot deliver something as a service. Open source community can deliver their project as a source code or binary package, but open source community cannot deliver something as a service because they don't have a platform for that. So all the cloud providers are providing, open source as a managed service. For example, AWS or Google or Azure, they have a bunch of open source project as a service. But we like to bring this role to the open source community, so open source community themselves can manage those cloud service. That's why we built the platform called Steroid, and we also want to fund open source developers when user launch the project automatically fund the developers. That's it. We have a link here, so anyone interested, you can take a look how we fund developers. And Open Data Studio is actually these Spark serverless implementations on the server side or container image and the client library. They are all under this project called Open Data Studio. This is an open source project, and this project is aiming to implement data service or data processing or machine learning software, open source softwares service on top of cloud as a service on top of cloud. And we are this project Open Data Studio is using Steroid as a platform at the moment. So this is an open source, and we actually not only have a Spark serverless implementation as a service here, but also we are working on many more data or machine learning related projects such as Ray or Jupyter, Zeppelin, and there are a couple of other projects that we are working on. So if anyone interested, feel free to ask a question or participate this project. And I added some reference or link to the documentations or project and source code here. So anyone interested in actual implementation and actual source code, you can take a look, and then you will find all the source code required to build these Spark serverless experiences in these links. So yeah, thank you. This is my talk, and thanks for listening. Is there a question and answer time?
Yes, thank you. We have I have a few questions myself, but first maybe we can go with the question from the audience. So you showcased the Spark with Python by Spark driver. What about like Scala and maybe other languages? Is it also supported, or is it Python only at the moment?
That's it. Good question. So today we only implemented on the Python environment. So today only Python, but I think there is no reason why we couldn't do the same for Scala or other languages like R. So as long as the languages support interpret mode or interactive REPL, read, evaluation, print loop, I think those languages are I don't see any problem to enabling the same. So we also hopefully we can also spend some time to create the same thing for the Scala and the other languages, but yeah, I think a contribution will be really helpful here.
Yeah, good to know. Just for a context, like how long it takes to develop such a system from start to whatever it is now, like an estimation of human resources put to it already. Yeah.
I think in our cases, because we have to go through trial and errors, and we actually tried multiple different ways to isolate the workload inside of a Kubernetes cluster. So we spend some time to try a few different approaches. So we took actually more time than necessary. I think it took about maybe 2-3 months to build to have an initial working version. That doesn't include the Kubernetes platform itself. You saw access token and Kubernetes cluster management console on the website. That is not included, but just enabling or implementing Spark on Kubernetes, we spent like 2-3 months. But I think if you have a better understanding on Kubernetes and Spark cluster, I think you can cut a lot of trial and errors. And if you just follow the way we did, then I think it will not be very difficult. It won't take a lot of time on implementing this. I guess it of course it depends, but I guess it's no more than like 2-3 months if you follow the same way.
I can't hear Igor. Igor, are you here? Okay. We don't hear Igor, so I'll try to ask some questions myself. I'd like to ask about accelerating Spark with GPU, like because Spark 3, I believe, recognizes GPU as a first-class resource, and you can accelerate at least with NVIDIA hardware, but it's still quite hard and undiscovered area. Could you explain, is it possible to use GPUs with your technology?
Yes, the question is using enabling GPU acceleration. And let me try find a slide that is related to that. Actually, maybe, yeah, maybe here. So as long as your Kubernetes cluster have a GPU node pool or GPU instance support, you can of course leverage that. And the way we do is today we are on the process of supporting GPU enabled Spark, but the way we are working on is actually using the similar to this annotation label, pod label, and admission webhook. So we actually have not only this isolation, this is the name of label and the value of label, but also we do have a few different label that you can add to your executors pod definitions. So another label is actually another label that we do have is instance. So in the instance, user can select type of instance, and user can set GPU instance or standard large or standard small or standard extreme, extra large. So we have a additional parameter that user can configure to choose particular type of machines or resource, which is I didn't explain because we are working on that, especially for GPU. But I think Kubernetes actually supports node pool, and you can construct node pool with GPU-enabled machines, and another node pool with more memory, another node pool with more CPUs, and you can select a particular node pool using Kubernetes node selector or taint, and with tolerant definition in your pod. And in our way, we don't want the user to have a complex taint or tolerant configuration on their own pod's definition. So we just want the user add this simple label, and then this mutating webhook will automatically add necessary configurations to the executor pod's actual definition. So I'm not sure I explained it clearly, but that's how we wanted to support GPU or different type of machines.
Okay. Another question that I trying to ask is you mentioned some dependencies on Kubernetes API. And as far as I know, Kubernetes is very fast evolving thing. And all the things about Docker, deprecating Docker in Kubernetes, etc. So does it relate to you and your project? Does it conflict somehow, and how you deal with fast evolution of Kubernetes and container technologies?
I'm sorry, I lost a little bit of your
Yeah.
question. Could you repeat?
I asked if you depend on a Kubernetes API. What API it is? Is just a Surface API, or do you depend on some internal implementation? And what will happen if something in Kubernetes will change like tomorrow?
I see. I see. So what we are depending on at the moment today is a Kubernetes basic API, and I think that is a creating a container or pod or removing the pod. So those basic APIs are what we are depending on, and Kubernetes community is doing, I think, really well about versioning those APIs and keeping compatibility. So I think as long as using those basic APIs, I don't too much worry about changing the API change in the future in a non-compatible way. But I think there are also the additional capability that we are using, such as mutating webhook or pod security policies and quota, especially on mutating webhook or some details, such as we are using host port to make sure every executor is run in the separate VM. Those behavior, let's say some behavior changes in the future, the different way the work into the different way. So later, let's say Kubernetes scheduler internally changes their algorithm to schedule. So even if host port is the same, they can be allocated in the same VM. That I hope that's not happening, but can happen such things in the future. So I think some basic API I think we can rely on, but some very detailed features, some particular behavior that we are depending on, we expected that that could be changes as Kubernetes improves or evolves. So we are actually focusing on making automated integration test. So we automatically test all the our expected behavior on the actual target Kubernetes cluster. So we always make sure we have the same behavior we want.
And Igor is with us. So Igor,
Yep.
hello.
Can you hear me? Right.
Yeah. Yeah.
Cool. Yeah. So I have a follow-up question on what we were discussing about GPUs. So say I have a particular job that I want to run that requires some dependencies on like third-party libraries with particular versions. When you have an on-premise Kubernetes cluster, it's usually very hard to, or like not even a Kubernetes cluster, but just a Hadoop cluster. It's hard to convince your data engineers that you need a particular version of something installed on the particular machines. And then you end up like building up your dependencies and bundling it as a separate package. So how that solves here? Do you modify the Docker container for the executor, or can you just provide the list of dependencies when you create a session? Something like that?
That I think that's also a great question, and we are also trying to provide options, multiple options for that. I think the first option is, of course, if the dependencies are publicly available, of course, user can add load packages via Spark configurations. That's the first way. I think another way is we are also thinking adding a feature or capability, something like a bootstrap script. So user can add a bootstrap script, and that will run on every executors before they actually initialize. So user can install some additional libraries or configure different way if they want. So that's another one that we are looking forward to it. And the last one is, of course, user can have a customized container image. So user can, we also open sourced our container image project or container image build script. So you can find the container image, and of course, a user can modify and build their own container image and set that particular container image to spin up a Kubernetes Spark cluster here. So those are three different ways that we think we can support the custom dependencies or managing dependencies. But I think if there is a better way to do that, we love to learn and use that way, because of I think this is a very common problem or challenges that a lot of users want to use different dependencies or sometimes a private repositories. So we'd like to learn more on this area.
Okay, I think we have one more question from the chat, and it's regarding if the Kubernetes cluster doesn't have enough resources for the app, then what's going to happen? Like, for example, there are a few users that run different apps on the same cluster.
So the question is, when Kubernetes doesn't have enough resources, but users wanting to run some workload, right?
Yeah, I think that's the question. Yeah.
And so I think it depends on your Kubernetes cluster configuration. But let me assume that your Kubernetes cluster is configured to allow scale out automatically. In that case, once, let's say, a user created more Spark executors, and Kubernetes doesn't have enough resource to create actual instance container or pod, then Kubernetes cluster will automatically add more nodes, provision new node, and add more nodes into the cluster. And finally, your executors or users' executors will able to schedule to the new node. That's it. But it depends. So some Kubernetes cluster is not configured to auto scale in that way. In that case, users work will wait until other users' work finishes and free up some resources on Kubernetes cluster.
Good to know. Okay, and I guess that would be the last question, and then we go to the expert zone. So you, at some slide, you showed that you support like Python 3.6, 3.7, and 3.8. And a couple of months ago, 3.9 was out, and I think it's not yet supported by PySpark. But how long usually the adoptance? What's your estimation? Like when it will be possible to use that new Python version?
I'm not 100% sure. I'm not. Maybe I'm wrong. So I'm not 100% sure which version of Python is supported by PySpark. But as long as PySpark support Python version, let's say 3.5 or 3.9 or any version, just supporting in the point of view of a Spark serverless implementation here, it's just a matter of adding one more line or one more environment in the container image, and add another line to set that version in the client library. So supporting additional version is really easy in serverless Spark point of view. So actual difficulties are on the PySpark side, which version of Python that PySpark implementation can support. That's it. It depends on that.
Mm-hmm. Okay. Well, thanks. I guess time is up, right? And we should go to the expert zone. Zoom discussion. Cool. Thank you.
Okay,
Yeah,
thank you.
thank you.